In this video, we are going to introduce matrices. We are going to use matrices to solve systems of linear equations. We're going to define a column vector and the zero vector. We're going to define input matrices in row echelon form and reduced row echelon form. And then we're going to solve a system of linear equations using the row reduced echelon form. So first of all, let's explain what a matrice is. A matrice, that is an M by M matrix, is a rectangular layout of numbers from C. These numbers are from the complex numbers, but remember we talked about this yesterday, that when we're talking about the complex, we're mostly in this class in real numbers, and in particular we are in integers. Having M rows and N columns. When we use matrice notation, we typically note the matrice as a capital A, B, C. We usually choose our names for our matrices at the beginning of the alphabet versus the end of the alphabet. And we usually, when we talk about a matrice, we will usually either use these big brackets here, like this, to denote that where you're looking at a matrice. Sometimes you'll see them with very large parentheses. So if we take a look at our system of equations that we had yesterday when we talked about a system of equations, this particular system of equations would become an M by N plus 1 matrice. This position, which is the A11, means I am in row 1, column 1, and it comes from the first equation with the first coefficient on the first equation. A12 is this A12, and etc. It is the size of M and N plus 1 simply because of the fact that we have M equations and then we had N variables, but we still have, in this example of a matrice, we did add on these constants. So that's how come it is an M and an N plus 1, even though we had N number of variables. It has M rows, N columns, so the first time you see it, it is an M, comma, N plus 1. The M, the capital A with M, comma, and then N plus 1 represents the matrice. But when I put it in this notation, where it's in these brackets and it's IJ, that represents a particular number in row I and column J. So as an example, if I wanted to look at A and then 2, 3, then I want to go to row 2, so row 2, column 3. Okay, so when we are looking at a matrice, if we have a matrice that has only one column and it has M number of rows, we're going to call that a column vector, which is basically just a matrice that has one column. The column vectors are usually wrote in bold. So when we're talking about column vectors, we usually just even call them vectors. The column vectors are usually bolded. However, it can also be with a bar, this arrow, or a bar across the top. Arrow is what we usually use. So that this U may be noted this way with a bold, or U with arrow. And sometimes they have the U with a tittle. That's a tittle. I love saying that, a tiddly tiddly. It's a tittle. So that is a tittle underneath. All of these are notations for column vectors, or in other words, just a vector is what we're going to call them. And then what a solution vector is, or the solutions to our equations, it's a vector, is going to be the solutions that satisfy all of the equations. And in this case, because if I have n number of variables, if it is a solution, if the system does have a true singular solution, and it's not a one that is dependent on other things, so it isn't one that is, it is not a dependent solution, and it's not obviously a no solution, it should have n number of pieces in the vector, so that it is a size n. So it should be one column with n number of entries or n number of rows. So when we're talking about a solution vector, what we're really talking about is a list of variable quantities at a singular point, or it could also refer to the solution to that system of equations. So when we say a solution vector, be aware that it could kind of have two different meanings. So now if we go back to our system of equations, If we wanted to look at only the constants, then only the constants would be just this b, and the vector that would be formed is the b with a bar. Now, I said earlier that we usually use u and v and w, but sometimes we will use b when we're talking about the constants in a system of linear equations. So this b is the constant, and then for each entry or component of the vector b, we should have m entries, because remember we had m number of equations. And then of course when I see it in this form, this is the entry that I'm looking at. So when I see it with these brackets and the vector I'm looking at and then the I, it tells me the position I'm looking at. So I could be anywhere from 1 to m. So I could have, as an example, if I wanted to have in this notation b with a vector notation, and I'm talking about 3, then I'm asking for the third position, the thing that is listed in the third place, the third row. Okay, and then the solution to this, the solution to the vectors, is notice how it is done with an x typically, because we're usually using x's as a variable. Now we can use anything, x, y, z, but if we use x, y, z, then we can only go with 3 unknowns. So we can only have 3 equations at the most. I mean, at most we can have 3 unknowns. And there are going to be times which our vectors do not necessarily represent planes. So we will want to go beyond the x, y, z. So when it's in the solution would be in this form, where you've got my x vector is my solution, and my first solution for in the first variable, the second variable, third variable, all the way up to however many variables that you are looking at. Also, we're going to take a moment and talk about the 0, or the 0 vector. The 0 vector is, again, a vector, or a column vector if you like, in which every entry is 0. Now notice this is bolded. If I wanted to, I could have put the arrow above it to let you know that I am talking about a 0 vector. So again, I'm using that same notation for consistency. If I see 0, and that should be a subscript I, is equal to 0 for every single entry between 1 and however many lines I need, however many rows that I need. Now, when we're talking about a matrix, and we're talking about it in terms of solving, there are parts to the matrix. The first part is the coefficient matrix. And what the coefficient matrix is just the coefficients being pulled off, not adding that extra column of where the constants are. So if we look back at our linear system, then what we have here is just the coefficient matrix A would be A11, A22, all the way down. Now this may or may not be a square matrix. It's a square matrix if I have the same number of variables as I do equations, then it would be a square matrix. If it's not, if I don't have the same number of variables as I do equations, then it will not be a square matrix. It'll just be a rectangular matrix. Now when we're talking about matrices, when we're talking about the linear equations, and one way that we want to talk about the linear equations is you're going to see this notation. This LS is notation for the fact that I'm looking for a system of linear equations. We also refer to this as a matrix representation of the linear equations, where the A is the coefficient matrix and B is the column vector, or the column vector, which is the constants. So you may see the notation like this. This is meaning the linear system of equations. Now, the first matrix that I showed you up above is what we have called the augmented matrix. It takes your coefficient matrices, your coefficient matrix, and adds on that column vector, or in other words, it adds onto it the constants on the last column of the matrix. And you'll see it wrote like this. So this notation means that I am looking at an augmented matrix. Typically, we will put a bar between the coefficient matrix part and the constant matrix. So if I go down here and look at my matrix again, what I should see by tradition is having a bar right there between those two to let me know that this is an augmented matrix, and everything on the left side of that bar is all the coefficients, and everything on the right side is the constants. So this is what we usually use, is the augmented matrix when we are going to be solving systems of equations, but we don't have to. Sometimes we're going to use just the coefficient matrix, and we're going to separate it from the constant matrices, and we'll go into why we'd want to do that later. In fact, we'll do some examples later in the quarter. So when we're talking about an augmented matrix, it is just that, it's just a matrix. It is no longer a system of equations, and the only connection that we have to a system of equations is the location of the coefficient in terms of the matrix. So the augmented matrix in and of itself has no solutions. This right here is not giving me any solutions. It's just an augmented matrix. What I can do, though, to get solutions is I can do row operations. Just like before in yesterday's video when we were solving the systems and we were able to add equations together and multiply equations by non-zeros and all of that, we are going to do the exact same thing here with our matrices. So what we're allowed to do is we're allowed to swap the locations of two rows. We can swap row 1 with row 2 or row 5 with row 7. And the way we note that is we say row, and then this I just tells me which row I'm going to take, and this other J just tells me the other one. I'm just going to switch those positions. What I'm also allowed to do is to multiply any row with a matrix by a non-zero number. We will note it as alpha just being our constant that we're going to multiply that row by. So it's going to be our like 5, row 3, and then we're going to put the answer back into row 3. You always have to tell me where you're going to put those answers. We always note it as where does it go. It's easy to do it this way because we can follow through and say, oh, I can see my mistake. I did not put the answer back where I had noted it. Another thing that we're allowed to do is we are allowed to, just like with our equations when we're not in matrices, is I can multiply any row by a non-zero constant and then multiply an additional row by a non-zero constant or not, and then add those two rows together. But I do have to tell you where I'm going to put that. So that's what this denotes. So I'm going to take 3 times row 1 plus 5 times row 3. I'm going to put the answer back in to row 3. When you do this type of operation, when you're taking one row and you are adding or subtracting it to another row, you need to put it back into one of those, the solution to that, the end result to that, into one of those two rows that you were messing with. So that's why you have to put it back into one of those two rows, and it's a good idea to always note where it's going. So we say that when we've done all these row operations that the two matrices are equivalent if one can be obtained by a sequence of row operations from the other. So when I take one and I mess around with it to see if I can get the other one, then if I can by the row operations, then I know that they are row equivalent matrices. So let's take a look at this example right here and see if I can get one matrix to equal the other one by just row operations. So the first thing I'm going to do is when I look from A and I look to B is I look to see if any of the rows are exactly the same numbers, but maybe in a different position. As I take a look at this, I note that this row, which is 2, -1, 3, and 4, is this row here. So what I'm going to do is I'm going to go ahead and take my row, my A, and I'm going to tell you that I'm going to take row 1, I'm going to switch it with row 3. So then my A matrix then becomes, I'll have 1, 1, 0, 6. The 5, 2, -2, and 3 I've done nothing to. 1, and then this becomes 2, -1, -2, and 3. So now this row is equivalent to what I've done. The next thing I'm going to do is say, okay, I look at row 1. Oh, look, row 1 now matches. So row 1 and row 2 in the B matrix is matching my A matrix by just changing those two rows. So then it's a matter of, can I get a row 2 by a combination of adding or subtracting row 1 multiplied by something and adding it to row 2, putting the answer back in row 2, or taking row 3, multiplying it by something, adding it to row 2, and putting the answer back into row 2. So if I take my first row and I multiply it by a -2 and I add it to row 2, put the answer back into row 2, I'm going to get that row 3. And I know that I wanted to do that because I want this to be a 3. If I take and just multiply or just do a subtraction here, row 2 minus row 3 back into row 2, I'll get a 3 there, but I'm certainly not going to get a 0 in that position. So I know what I'm not going to do is I'm not going to do, okay, row 2 minus row 3 back into row 3, because it's not going to satisfy the second position in. So I know that is not what I'm going to do. However, if I take row 1, so if I take row 1, multiply it by 2, and in fact I'm going to multiply it by a -2, and then I'm going to add it to row 2 and put the answer back into row 2, I think that's what I'm going to get for my row 2. So then if I do that, then what I'm going to have, my first row, even though I multiplied it by 2, I'm not putting the answer back into row 1. So row 1 has not changed. So it's 1, 0, and 6. Row 3 has not changed. So it's -2, -1, -2, and 3. Now, what I'm going to do is I typically will use a lighter colored pencil or maybe even a different colored pencil so I can do that -2 multiplication up into the side of my initial row. So this becomes a -2, -2, 0, and -12. And that just makes it easier for me that when I actually do add those two rows, I notice that it is the -2 plus 5. That -2 plus 5 gives me the 3. That checks off. Then I do the -2 plus 2, which is 0. That one checks off. So this is looking good. And then I do 0 minus 2. That gives me -2. That one checks off. And then I have -12 minus 3, which is -9. So these two matrices are row equivalent. And that's because I was able to take one matrice, add and subtract rows, multiply rows, switch rows, and get the other matrice by just doing those 3 allowable row operations. Let's take a look at our theorem of row equivalent matrices. Our row equivalent matrices, this is a theorem. The proof is in your book for your viewing pleasure because I know you'd love to go through it. And again, I'll be honest, if you all want to go through it in class, I would be happy to go through it in class. If not, read through it. Let me know if you have questions. So suppose A and B are row equivalent augmented matrices. That means augmented again means that I've added on that column vector, which is the constants. Then the system of linear equations represents our equivalent systems. So let's talk about what we want to do. We have reduced row echelon form. And I want to talk, before I talk about reduced row echelon form, let's talk about row echelon form. So I'm going to take a moment, I'm talking about row echelon form. And when we're talking about a row echelon form, is you have some matrix in which all of the numbers underneath the 1, 1 position are all zeros. And in the 1, 1 position, it is a 1. Now you could have some numbers here, that's okay. All the way down to here, that's okay. Then in the 2, 2 position, that's also a 1, and then underneath that is all zeros. And then again, you can have some numbers here, no problems there, all the way to there. And then in the next 3, 3 position is 1, and again, zeros underneath it. And basically what a row echelon form is that in this diagonal, all of the 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 positions are all 1s, and everything below it is 0. And in fact, if you think about it, this is what the Gaussian elimination looked like when we were doing that in yesterday's video. Now let's take a look at what it means to be in reduced row echelon form. So basically what the first one is saying is if there is a row of zeros, it has to be at the bottom. It has to be below any other row that doesn't have an entire row of zeros. That's what number 1 says. Number 2 says that the leftmost non-entry 0 of the row is equal to 1. So what that means is if I take a look at this over here, which is in the row the row echelon form, that's talking about this, that the first time you see a non-zero number in that row, it had better be a 1. That's what number 2 is saying. Number 3, the leftmost non-zero entry of a row is the only non-zero entry in its column. And what that means is that I'm not going to have a number above and below. So unlike over here when I'm in the row echelon form, where I was able to have a 1 here and a number above it, number 3 says that if I'm in an entry where I have a 1, I better not have anything above it or below it but zeros. That's what number 3 is saying. Now if we take a look at number 4, consider any 2 leftmost non-zero entries, one located in row I, column J, the other located in row, and that should be S, row S, and column T. If S is greater than I, then T must be greater than J. And what that's saying is that I can't have, for this to happen, for this to be in the reduced row echelon form, what I can't have is a matrix that looks like this to be in a reduced row echelon form. I can't have 0, 1, 0, 0, 5. And then 1, 0, 0, 0, 3. And even just that. That is not in reduced row echelon form because it fails number 4. Number 4 says that these 2 rows need to be switched for this to be in reduced row echelon form. Now we're going to talk a little bit about what a pivot is. So you're going to hear this later when we start really working in matrices, we're going to talk about a pivot. And what a pivot basically is if it's in a row or reduced row echelon form, then the column that contains that 1, the first time you see that 1, and it's zeros below and zeros above, is the pivot column. And the number of non-zero rows will be denoted by R. This is also equal to the number of ones that we see, the leading ones that we see. This should be equal to the number of pivot columns. So if I look at this example here, that this, once it's in the correct form, which would have been 1, 0, 0, 0, 3 and 0, 1, 0, 0, 5, that this is a pivot and this is a pivot, and my R would equal to 2 because I have 2 rows that have pivots in them. Now if I take this and add on a row of zeros, I still have an R2 because I still have 2 rows with non-zeros in those positions as ones. So adding a row of zeros is not going to change the number of pivot columns that you have. You just have 2. R is 2. Adding a little bit more notation here. When we talk about the pivot columns, the column indices for the pivot columns will be noted as D, and this should be a D sub 1, that should be a subscript 1, that should be a subscript 2, subscript 3, and subscript 4, or excuse me, R, where D1 is the first column, first row. D2 could be the second column, second row. And so that when you are looking at these have to be, the DR must be the largest, so like the largest row, if you want to think of it that way. And why the columns are not pivot columns, the ones that are not pivot columns will be denoted as Fs, F sub 1, F sub 2, F sub 3, F sub n minus R. Where in this example over here, I have this is F sub 1 because I have one row that does not have a pivot column in it. Now let's take a look at this example here, where we're trying to determine if they're in row echelon or row reduced echelon. Way that we defined very loosely row echelon form is it needs to be ones and in the diagonal part of it, or possibly zeros if you have a row of zeros. And you can have numbers in other positions. So if I'm looking for row echelon, then this one is in row echelon form. And let me see. This one is in row echelon form. This one's not because of that 1 being there. Now, if I take this matrix right here and I divide everything by 2, if I take the matrix and divide it by 2, it would also be in row echelon form. This one's not because I don't have a 1 in the 1, 1 position. I have a 0. If I would have switched those two rows, that would be in row echelon form. I take a look at this one, and this is not even close to being in row echelon form. Now, which ones are in reduced row echelon form? Now, this one, again, if I were to switch it up, so I'd take row 1, goes down to row to the bottom, and I take row 2 up 1, I take row 3 up 1, I take row 4 up 1, then that would be in reduced row echelon, but in its current form, it is definitely not. Now, the last one is the second one is again actually in reduced row echelon form. And you're thinking, but wait a minute, it doesn't actually hold true. Well, let's go through all 4 of the things that have to happen for row echelon. There is a row where if it is a row of zeros, it's in the bottom. Okay, we don't have to worry about the number 1. Number 2, the leftmost non-zero entry of a row is equal to 1. Okay, so that's true, that's true, that's true. The leftmost entry of a row is the only non-zero entry in its column. So this is the only one with a non-zero. This is the only one with a non-zero. This is the only one with a non-zero. And this one is the only one with a non-zero. So that 2 doesn't have anything besides 0 in that row, in that column. The other ones only have the 1s and 0s in the column. So we've got that one, we got that one, and we got that one. The last thing that has to hold true for it to be in reduced row echelon form is that let me just erase that, is that the 1s have to be descending. So as you look at it, I can't have like the one that I did here. This one is not in reduced row echelon because it fails the fact that this 1 is not in the 1, 1 position. So this 1 is in the 1, 1 position, is the most left one. And then the next one can be down 1, or it can be down, or excuse me, over 1, down 1, or it could be over 2 and down 1. But this also is the place in which I have that 1. And then the last one, of course, that one. So there are 3 that are in a reduced row, or excuse me, there are 3 that are in row echelon form. And there's only one of these that is in reduced row echelon form. Okay, so let's go ahead and solve these by doing the RREF. So the first thing I'm going to do is I'm going to put these into a matrix. So I'm going to do the equivalent matrix here, and I'm going to do it with the augmentation. So my first equation is 0 because I don't have an x sub 1, 1, 5, negative 4. And then I have 1, 4, 3, negative 2, 2, 7, 1, negative 2. Now, what I'm going to do is I'm going to switch row 1 and row 2. And the reason I'm doing that is because I've already got a 0 then right below that 1, and I have a 1 in that 1, 1 position. So then this becomes 1, 4, 3, negative 2. 0, 1, 5, negative 4. I need to make that slightly bigger. And this is 2, 7, 1, and negative 2. Now what I'm going to do is I'm going to take negative 2, row 1, and I'm going to add to it row 3. I'm going to put the answer back into row 3. Now the reason I'm doing that is because I need to have a 0 right there. So like I told you before, what I'm going to do is I'm going to write the smaller multiplication up here so I can remind myself this is negative 2, negative 8, negative 6, and positive 4. So then this becomes 1, 4, 3, negative 2, 0, 1, 5, and negative 4. And then I'm going to do this addition, and I get 0, I get negative 1, I get negative 5, and I get 2. Oh, and I should have that bar. Man, I just get so excited I don't put that bar there. So now what I'm going to do is I'm going to go ahead and add these two rows. So what I do is I use row 1 to turn it into a pivot column by putting everything below row 1 into zeros. Once that everything below row 1 is in zeros, I'm now going to take this second row and make sure I can get a 1 there and make that my pivot column. So I need to get a 0 below that, and it's just a matter of adding these two together. So I'm going to add, what I'm going to do is I'm going to take row 2 plus row 3. I'm going to put the answer back into row 3. Now notice I don't do anything with this. 1, 4, 3, negative 2. 0, 1, 5, negative 4. Now when I add these two rows, I'm going to get 0, 0, 0, and negative 2. And I'm going to stop. I'm not even going to try to put it in reduced row echelon form because right here, this is a false statement. This is telling me 0 is equal to negative 2. That's a false statement. So this is a no solution. No solution. So I'm not even going to try to put it into reduced row echelon form. Let's take a look at the next example. So what I'm going to do is I'm going to go ahead and erase all of this over here so that, excuse me, so that I can have the space. So I'm going to erase all of this. Let me move this over. So let me erase this. We know that's a no solution. Let's see what happens with our second solution set here. And so with our second one, what we're going to do again is throw this into a matrix, and it's going to be 2, 0, negative 6, negative 8. Anytime you have a variable missing, you're going to put a 0 as a placeholder. 0, 1, 2, and 3. 3, 6, negative 2, negative 4. Now what I'm going to do is I'm going to go ahead and take row 1. I'm going to subtract it from row 2 and then put the, row 3 and put the answer back into row 1. Because what I want in a reduced row echelon form is I need to have right there, I need to have that to be a 1. So I'm going to take row 3, I'm going to subtract off row 2, I'm going to put the answer back into row 2. So then this becomes 1, 6, negative 2 minus a negative 6 becomes a positive 4. Negative 4 minus a negative 8 is going to be a positive 4. My second row I didn't do anything with, so that's 0, 1, 2, 3. My last row is 3, 6, negative 2, and negative 4. Now again, this is my pivot right here, so I need to make this to be a 0. So what I'm going to do is I'm going to do negative 3 row 1 plus row 3 back into row 3. So this would be a negative 3, negative 18, negative 12, and negative 12. So then this will be 1, 6, 4, 4, 0, 1, 2, 3. And I keep forgetting that. Put that bar right there. Put that bar right there. Okay, and now I'm going to go ahead and do this addition, and this gives me 0 here. This is negative 12, and then negative 14, and then negative 16. Now what I'm going to do with this last row, because I like to work with smaller numbers, is I'm going to go ahead and take row 3, and I'm going to divide it by a negative, well, I'll leave it negative. I'm going to take row 3, and I'm going to multiply it by a 1/2. Put the answer back into row 3. Not a necessary step. I just like working with smaller numbers. 1, 6, 4, 4, 0, 1, 2, 3. This becomes 0, negative 6, negative 7, and negative 8. All right. Now, this is my pivot. So I'm done with row 1. I use row 2 to make this become 0. And the way I'm going to do that is I'm going to do 6 row 2 plus row 3, put the answer back into row 3. So this becomes 6, and this would have been 12, and this is going to be 18. So I have 1, 6, 4, and 4. Don't forget that line. 0. This is 1, 2, and 3. Remember, I'm putting the answer back into row 3, so I didn't actually change row 1. And then 0, 0, 12 minus 7 is 5. 18 minus 8 is 10. Okay. Now, if I wanted to solve the system and just be done with it, I am almost done. All I would have to do is to get it into row echelon form is this step right here, was that I'm going to take 1/5 row 3, put the answer back into row 3, and then I'd be in row echelon form. Then I could do some back substitutions, and I would be done. So this would be 0, 0, 1, and 2. So this is now in row echelon, but it's asking me to do this in row reduced echelon, or reduced row echelon form. So to be in reduced row echelon form, I need this to be 0, I need this to be 0, and I need this to be 0. So to put it into reduced row echelon, what I do now is I use row 3 as the pivot going upwards. So I'm going to use row 3 to eliminate what's in row 1 and row 2, column 3. So what I do then now is I'm going to take -2, row 3 plus row 2, and put the answer back into row 2. Simultaneously, I'm going to do -4, row 3 plus row 1, put the answer back into row 1. Now notice I'm doing this one simultaneously. So then what I'm going to get then is the last row is now stable. I'm not changing anything there, even though I am, but the answer is not going in that row, so I'm really not. So then this first time becomes -2, and this one becomes -4. When I add these two rows together, I'm going to get 0, 1. This is going to be 0, and this is going to be -1. I'm going to do that again, now with my -4. So I have -4 times 1, -4 times 2, which is -8. I'm going to add that to row 1. So in row 1, I'm going to get 1, 6, 0, -4. And I'm done now with row 3. The only thing I have left to do is make this 0. So I use row 2 to make that a 0. So I do -6 row 2 plus row 1. The answer goes back into row 1. So row 3 I didn't do anything with in this step, so it's going to maintain the same. Row 2 I'm really not doing anything with it because I'm not putting the answer back there. So then all I have to do now is do like I did before. This is going to be -6, this is going to be 0, and this is now going to be +6. I'm now going to add those two rows together. So I get 1, 0, and then 0, and 6 plus -4 is +2. So now it is in reduced row echelon form, and I can tell you what the answers are right out of the gate. So this is x sub 3. X sub 3 is equal to 2. So if I write this as a solution vector, then my x vector, or my solution, is going to be 2, -1, and 2, where this first one represents the x sub 1, the second one represents the x sub 2, and the third one represents the x sub 3 solution. So if you're thinking about it in terms of x, y, z, you could have wrote this as 2, -1, and 2 if it was in terms of x, y, and z. This is the solution vector. Okay, let's go back to my last example here. That was a long one. Now on this one, what's happening on this one is when I put this into a matrix, I have 1, 3, -3, and -3. I have 0, -2, 0, and 2. The problem is I have three unknowns, and I only have 2 equations. What we know for certain, though, is that we know from this row right here that x sub 2 is equal to -1. That we know for certain. So if we know x sub 2 is equal to -1, and then if we put that into the first equation, we're going to get x sub 1 plus 3 times -1 minus 3x sub 3 is equal to negative 3. What that tells me when I go ahead and solve this, I have x sub 1 and then minus 3 and then minus 3 x sub 3 is equal to negative 3. I'm going to go ahead and add 3 to both sides, and I'm going to get x sub 1 minus 3x sub 3 is equal to 0. Then I have x sub 1 is equal to 3 times x sub 3. So what the solution then is going to be x sub 1, or excuse me, x sub 3 will be the independent one. And what we call that is a free variable. So it's the one that is free, and x sub 1 is dependent on x sub 3. So the solution to this one, x arrow, or you might write this as the solution, which is equal to, and you might see it in this notation, is I have 3x sub 3, that's what x sub 1 is. I have negative 1, because that's x sub 2. Then x sub 3 is the free variable. So I put it like that. And then I'm going to tell you all about x sub 3. Well, x sub 3 belongs to the complex numbers. And so that's the solution for that. And I can find that by doing row operations, but in this case it would have been much easier not to. So the free variable is x sub 3. And we call it the independent. Let's go ahead and look at a couple of more theorems, and then what we'll do is do another example, and then we'll call it a night. So the first theorem we have is row equivalent matrices in echelon form. Suppose A is a matrix, then there's some B matrix so that A and B are row equivalent, and not only that, but B is in reduced row echelon form. What the heck does that mean? Well, okay, that means back here, this one, when we finally got done with it, where did the heck did that go? Because I know that we did it. It was the most interesting thing that we did, and it's gone. Where did it go? It's gone. When we were working on this, if you remember, I ended up with the matrix that when I ended up with this matrix that is now gone, that it is equivalent to the one I started out with. That's what that theorem says. Next theorem is reduced row echelon form is unique. Suppose we have this matrix A. It's an n by n. That's the one that I did that has now disappeared. I don't know where it went. It went into the ether. And B and C are m by n matrices that are row equivalent to A. Then in reduced row echelon form, B has to equal C. That has to happen. So what does that mean for us? Well, let's look at these two matrices. Row reduce each matrix and then determine whether or not the reduced row echelon forms of B and C are identical. From this, we're going to argue that B and C are row equivalent. So what we're going to do is, by the magic of marker, rather than you all watch me go through this again, I'm going to go ahead and give you what it looks like with all the row operations. The B matrix is equal to, with all of my magic that I've done all before, is 1, 3, negative 2, 2, 0, 1, negative 3, and 1/2, 0, 0, 0, 1. That's what that looks like in row reduced form. Now let's take a look at C. C in row reduced form is 1, 2, 1, 2, 0, 1, negative 3, 2, 0, 0, 0, 1. Now, what does it look like? Because right now this is in row reduced form. These are both in row reduced form. We're now going to take a look at what these look like in reduced row echelon form. The B matrix is going to be equal to 1, 0, 7, 0, 0, 1, negative 3, 0, 0, 0, 0, 1. The C matrix will be 1, 0, 7, 0, 0, 1, negative 3, 0, 0, 0, 0, 1. So what does that tell us? Well, if we look at our previous two theorems, we know from our previous two theorems that these have to be row equivalent. If we look at these theorems that we just talked about, reduced row echelon form is unique. Since it is unique and they are equivalent, that means if we look at our forms, this is a reduced row echelon form, reduced row echelon form. These are equivalent. That means that these are row equivalent. They have to be. So that's it.